2212, Lab 6 by Connor Wynn. Now, introduction. The purpose of this lab is to measure the effects of a magnet falling through a conductive tube and then create a computational model of that magnet falling through the same tube and then compare the results. Methods. We recorded the time of the magnet falling through an aluminum tube and then we created a computational model of that magnet falling through the same tube. Results. Experimental model was 1.68 seconds from the magnet falling through the tube, and a computational model was 1.907 seconds. Principles. The Biot-Savart law, the dipole magnetic field, Faraday's law, and Newton's second and third law. The Faraday's law is the induced voltage equals negative N times delta flux divided by delta T. The N is the number of loops, and then that's the flux. The magnetic field is mu Ni divided by 2R, and I is the voltage. Now, Newton's second law is that the force equals the magnitude times acceleration, which is important for gravity. Instead of acceleration, it's gravity. And Newton's third law, which is that for every action, there's an opposite and equal reaction. Now, the model. The system of this experiment is the magnet, and the surroundings are the Earth's magnetic field and the aluminum foil tube. Now, the forces for consideration is the field from the induced current from the tube, and also the field from the Earth, the magnetic field from the Earth, and gravity. Now, we use an aluminum foil tube instead of a completely metal tube, as the magnet would get stuck inside the tube. So we use an aluminum foil to replicate the magnetic fields. Now, experiment. For Faraday's law, we wrap the tube with aluminum foil and adjust it so it's vertical from the ground. And then we drop the magnet down the tube at the top and recorded the time it takes for the magnet to exit the tube. And repeated this for a total of 5 recorded instances. Now you can see here we have done 5 trials, and the average time for the magnet is 1.68 seconds. Now, the 2 dimensions. As I said, the average time was 1.68 seconds, and the length of the tube was 0.465 meters, and the width of the tube was 0.019 meters, and the inner radius is 0.013 meters. Now, the dipole moment is 3.51 Nm divided by T, and then the mass of the magnet is 30 grams. Now, experiment code. Now, we plugged in the resistance of the aluminum and the gravitational constant, and then we plugged in what the length, width, and radius was for the tube. And then after this, we had to plug in the mass and the magnitude of the magnetic dipole moment. And then we created a function to calculate the magnetic field of the bar magnet. And then once we found that, we calculated the derivative of the flux, magnetic flux due to the falling magnet. Now, and then after that, we made a function to represent the simulation loop. And then we calculated magnetic force from the tube onto the magnet. And as you can see here, this is a representation of the simulation. Now, the red means that it is going counterclockwise, and the blue means that the field is going clockwise, or Lenz's law. Now, if the systems were flipped, the speed wouldn't change, but the current would flow the opposite way. As we found out, the higher velocity magnitude equals a stronger current/force, and the steady state is reached when the forces are equal. Now, from our experiment, it is 1.68 seconds, and the computational time is 1.907 seconds. Now, the differences may be due to air resistance and other factors, and some errors include human time recording error and inaccuracies in ruler measurements. Now, whether the resistance of the conductor was reduced as possible to 0, now we use Ohm's law, which is V equals IR, where a lower resistance equals a higher current, which would equal a stronger force and a lower fault. And if holes or slots were cut into the tube, it would disrupt the circular current, and which means it would be less perpendicular to the force, which means it would be less magnetic force, and it would be a faster fall of the magnet. Thank you.